right, welcome to the introduction to rotational motion. So as part of our video, we're going to fill out this table that's going to make a comparison between linear and angular motion equations. But first off, let me talk a little bit about some of the terms you might hear. For linear motion, you might hear the word translational motion. Okay, so translational motion might be a way to describe that. An angular motion is the same as rotational motion. Okay, so depending on the resource you're using, or as you're listening to my videos, I kind of use the terms interchangeably myself. So, some background. Okay, so the purpose of this sheet is to kind of fill in the linear and angular analogs. So that is the variables we would use for linear or translational motion, and then the variables we're going to use for angular slash rotational motion. Now, a lot of students get very nervous about rotation. They've heard it's really hard or difficult. Really, rotation is just everything we've already been doing, but we're now going to apply it to things that are rolling. So before we get to the chart, we're going to just talk about a couple of differences here. So translational motion is pretty much all of the kinematics and content we have covered so far. Again, translational just means linear motion. So, I don't know, a box sliding on the floor, for example, would be a linear motion. We use force diagrams for that because we can shrink this to like a point mass. What that means is every part of the box moves in the same way no matter what we do, okay? For rotational motion, we're now talking about things that are rolling, but we can also apply a lot of these concepts to things that are revolving around something. So the earth around the sun, the moon around earth. So when we talk a little bit more in another lesson about angular momentum, we'll be talking about this idea of orbital motion as well as things that are spinning or rolling. Okay. So rotational motion. So if I imagine this is a bowling ball, I tracked what's called the center of mass of the bowling ball. Now, every object that has uniform mass, its center of mass is basically in the center or the middle of the object, okay? A meter stick, the center of mass is going to be around the 50 centimeter mark because that's the middle of the meter stick. For rolling motion, if we tracked the center of mass as my bowling ball moved, we would notice that the center of mass has translational motion. But if we were to track a point on the outside of the bowling ball, so like somewhere here as the bowling ball rolled, we would see something like that, okay? The point on the outside, and basically any point outside of the center, is going to exhibit angular motion or rotational motion, okay? That's because every other point on this object is rolling in some way. All right, so we're going to apply some equations to this in a moment. I just want to remind you that one revolution or one rotation of something is going to be 2 pi rads or 2 pi r meters. Okay, so we're just talking about the circumference. And we're going to talk a bit more about these rads. The rads are the units for angular displacement. We're going to talk more about that in a moment, okay? The unit circle is where a lot of this comes from, so you should have learned that in pre-cal. So we start with 0 over here. Or if we've gone all the way around, well, let's go in order, okay? So then we go up here, and if we're going to describe this in rads or radians, this is where I get 2 pi radians. So if I did just this sweep of this little arc here, my displacement would be 2 pi radians. Okay, we can continue on, and I get pi radians on the directly across from 0. I get 3 pi over 2 radians down here. And when we get back to start, we're back at 2 pi radians or rads. Okay, so when we talk about angular motion in these objects going along a circular path or rolling or spinning, we talk about the displacement in terms of radians if we're talking about a rotational quantity, and meters if we're talking about a linear or translational quantity. It's hard to show in a video, but if you can imagine that we could open this circle up to get a linear displacement. Oops, did not mean to do that. So like if we could undo the circle right here and roll this out and look at the distance in meters, it would be the same as the circumference of the circle. Okay, so we're going to fill in a couple things on our fill-in for the previous page. If you go all the way down to the bottom of the page, we're going to fill in a few things there. Now, some of these things we'll be talking about in a minute. So right now we're kind of going to fill it in, and we'll fill in some details in a moment. So arc length, again, is that part I swept out right here. That is your arc length. And we're going to talk about this variable for angular displacement in a moment. But it's going to be theta. But now we're doing theta in radians. And it's going to be multiplied by the radius. Okay, now one thing you want to also think about here is this, how we're defining r, or the radius. It's not always going to be the radius of the object. It's actually going to be the distance from the axis of rotation. Okay, and when we get into torque and things like that, we'll be talking about that axis of rotation. But when we talk about r, we're not talking about radius in the purest sense, that it's the distance from the center of the circle to the outermost point. It's really going to be the distance from the axis of rotation or the pivot point. Okay, now that will make more sense as you get into torque, like I said, but just keep that in mind, okay? That it's not necessarily specifically a radius of a given object. All right, linear speed. We can find linear speed by just taking displacement divided by time, or if we are talking speed, it's a distance divided by time. Now, don't get confused with S for speed and S for arc length. They do like to recycle variables, but be really careful with that. Now, the arc length idea doesn't come into play a whole lot in AP Physics 1 where they use an S. A lot of times they're just going to call it a displacement and a linear displacement, and we'll talk about that some more in a minute. The tangential acceleration is just going to be your change in velocity over your change in time, just like we have been doing. And then radial slash centripetal acceleration, that is your v squared over r, or what we're going to see in a moment, we can do angular velocity squared times the radius. And I'm going to talk more about that angular velocity in just a little bit. And then the period, remember, is the time for one revolution, or spin, now that we have objects that might be spinning. And that is equal to 2 pi r, or the circumference, over the velocity. So remember, we can find velocity as 2 pi r over the period for something that's rolling or moving in a circle. Okay, so we can find the period by taking 2 pi r, which is our circumference, and dividing that by the velocity. Or we're going to see in a moment 2 pi divided by the angular velocity. We're going to talk a little bit more about this angular velocity and angular displacement when we fill out the top. Okay? All right, so those are just kind of relationship between linear and angular variables. We're going to go back up here. We're going to fill these in with our other variables. Okay, so again, linear is translational, and then angular is rotational. Okay, so we already have talked about how to find displacement for linear motion by taking final position minus initial position. And the units are meters, right? So our base units for linear motion are going to be meters, seconds, and kilograms. And our angular quantities are going to be radians or rads. Rads, seconds. And then we're going to be talking about this idea of a rotational inertia or moment of inertia, and that's going to be measured in kilogram meters squared. So we'll talk about that in a moment, okay? All right, so angular, I kind of already gave this away. We use theta for angular displacement, and it's found exactly the same way. The final angular um, position minus the initial angular position, okay? Now, the piece that's going to tie these two together is going to be the piece that takes us from radians to meters. Now, hopefully in math, you learned that radians are like a unitless unit. They're not actually a unit in the sense that a meter or a second or a newton is a unit. Another way to think about this, if the unitless unit idea is like, what? Is that irradians are, it's a unit, but its unit doesn't have any dimensions. Like we know what a meter is, right? We have dimensions we can measure that against. It's a dimension of length, right? Seconds are measured in the dimension of time. Radians measure an angle, okay? But they do it by dividing a length by a length. So this unit for angle is dimensionless, okay? So the thing that ties them together, that's what we mean by the bridge, is going to be the radius or the distance from the pivot, okay? So the bridge that ties them together is going to be r. That means I can take my um, angular displacement, multiply it by r, and I can get back to a linear displacement, okay? Or if I need an angular displacement, I would divide a linear displacement by that, and I ran out of space there. It's just rearranging that equation for algebra, okay, depending on what you need. Average velocity, of course, in the linear or translational world is just the linear displacement divided by time. Well, the angular velocity is represented by omega. It's kind of a curly W. And that's just found by taking the angular displacement divided by time. So it's not that we're doing new equations, but that we're doing equations we have already done before. And so, but we're just swapping out our linear or translational variables for our angular or rotational variables, okay? And then the thing that is going to bridge these together is also going to be that radius or distance from the pivot, in that you're going to take the angular velocity times the radius to get that angular velocity. Now, we already talked about the units here being rads for angular displacement, and the units for an angular velocity would be in radians per second or rads per second, whereas we would have meters for our linear displacement, okay? All right, and remember these are average velocities. You cannot use those to get an instantaneous velocity or a final velocity if you have acceleration. So that leads us to our average acceleration equation, which is just the change in linear velocity divided by time if we are talking about linear or translational motion. For angular, it's alpha, or what kids like to refer to as the Jesus fish, because it's kind of shaped by the like the Jesus fish, but it's called alpha. And alpha is the change in angular velocity over the change in time. And just like acceleration is meters each second squared, the angular acceleration is rads each second squared. And then the bridge, or the piece that ties the two together, is also the radius here. So basically, if I take any of my angular quantities for the kinematics portion here and multiply them by the radius or distance from the pivot, then I will get the linear analog of that value. Okay, so that's how we can go between the two. Now, the kinematic equations are the change in position is equal to initial velocity times time. Can't make the dots. Plus 1/2 acceleration times time squared. Well, it's very similar in the angular or rotational form, but we just swap out our linear displacement for an angular displacement. We get our initial angular velocity times time plus 1/2 alpha, or angular acceleration, times time squared. Okay. The next kinematic equation, final velocity equals initial velocity plus acceleration times time. Well, it looks exactly the same in the angular form, except for it's a final angular velocity equals an initial angular velocity plus angular acceleration times time. And then last but not least is the velocity final squared equals initial velocity squared plus 2 times acceleration times that displacement. Well, swapping those for the linear variables for the angular variables, the equation still looks pretty much the same, except for now it is the final angular velocity squared, which is equal to the initial angular velocity squared, plus 2 times the angular acceleration times the angular displacement. Okay, I'm going to add one other piece here at the bottom. So the linear variable we use for mass is going to be m, and it's measured in kilograms. Well, we have also talked briefly about how that mass is related to what's called inertia. So inertia in linear or translational motion has to do with an object's mass. It's just how hard is it to change that object's motion. For rotational form, we do a rotational inertia. And it's an I. And there is a general equation for this, which is mr squared. Again, that r being the distance from the pivot. This is where the units of kilograms times meters squared comes from. So that rotational inertia is a resistance to a change in rotational motion. So if you think about objects that are rolling, it's how easy or hard it is to start or stop that object rolling. You may also hear this called moment of inertia. You might also hear this called moment of inertia. Sorry, I'm not sure why my video stopped. So sorry for a weird transition there if you saw one. It's called a moment of inertia in some resources, or rotational inertia. It is on your equation sheet. Please note that rotational inertias are dependent on object shape. So if you're using mr squared, you would use that for a point mass. Okay, so like a person, you could use the mr squared. Some really small mass attached to something that's rotating. You're going to do some practice problems in class with some of those ideas. But if it's certain shapes, like a disc is going to have a rotational inertia of 1/2 mr squared. So you should have received a table of rotational inertias to help you, but you can also look them up on Google. Just be really careful about the resource you're using, because I have seen some that are incorrect on Google. So just make sure you're checking those against the one if you're on the SJS homepage, you can go into the topics page, and if you go into rotation, there's a table there with the accurate rotational inertias. Now, for AP Physics 1, they tend to either give you the rotational inertia, or you would have enough information in the problem to solve for the rotational inertia. Um, but they are giving you the equation this year, so with the test being new and kind of revamped, you could have to calculate a rotational inertia of something. I tell students, if you're not sure what to use, like you're not sure if it's 1/2 or 2/5 or 1/3, or depending on what object you're looking at, just use MR squared. The most you're going to lose is you would fail to earn 1 point for using an incorrect rotational inertia equation, but you would be able to get all of the rest of the points. So if all else fails, use MR squared. But again, you shouldn't have to memorize these rotational inertias. They should be given to you on the test, okay? One final thing I wanted to talk about is this idea of this rotational axis or axis of rotation or pivot point. I can have an object that pivot point or the rotational axis. So let's say I have a ring or a hoop here. That axis of rotation can be in the center. It does not have to be a physical part of the object. So if you had a donut that had a nice big hole in the center of it and you rolled that donut across the counter, the axis of rotation would be in the center of the donut, even though there's no mass or matter there. Okay, so keep that in mind. Your axis of rotation does not have to be a physical part of the object. And objects can also be rotated really about any pivot point. They don't have to rotate around their center of mass, although the tendency, if an object is going to rotate, is around its center of mass. But we're going to talk some more about those things as we get into torque and some of the other ideas in rotation. All right, as we go through the topics, we will continue filling out the table. With our other quantities, but just in case there is not a video with these filled in, Newton's second law in translational form is F net equals mass, oops, not divided by, goodness, mass times acceleration. In rotational motion, we have torque, which is represented by the Greek letter tau. And it is now, instead of mass, we use rotational inertia. Instead of linear acceleration, we use angular acceleration. Now, the bridge here is a little different. Instead of multiplying the rotational or angular quantity by the radius, we are going to multiply the force by the radius. Okay, so when we talk more about torque, we'll talk about that idea of the force acting at a position away from the pivot point. Okay, rotational kinetic energy, sorry, linear kinetic energy is 1/2 times the mass times the velocity squared. In rotational, and sometimes they tend to give these a T subscript for translational and R subscript for rotational. It's going to be 1/2 rotational inertia times angular velocity squared. So really the equations are not changing much. We're just swapping out those analogs. So instead of mass, it's rotational inertia. Instead of linear velocity, it's angular velocity. Work, it's still just a change in energy, but we can also calculate work by taking that force times displacement. You also have that cosine of theta in there. Keep that in mind. We'll work on the torque side. It's just going to be torque times a angular displacement. Okay. The spring force doesn't come up much in AP1, but remember it's the spring constant times linear displacement. Well, for the torque on a spring, it would just be the spring constant times an angular displacement. Okay. Continuing on to the spring potential energy. Again, 1/2 kx squared versus 1/2 k theta squared. And then momentum is mass times velocity. Angular momentum is represented by the letter L, and it's rotational inertia times angular velocity. Just like linear momentum is mass times the linear velocity. Now, the bridge here, angular momentum is equal to linear momentum times the radius. So we can also represent an angular momentum with mass times a linear velocity times that radius. Now again, remember the radius here is distance from the pivot, okay? Conservation of momentum still holds as long as the net force on the system equals 0. Then we have conservation of linear momentum. We also have to have conservation of angular momentum. Okay. Remember, we can also calculate a force with a change in momentum over the change in time. Remember, really, Newton's second law is really the change in momentum over the change in time. He actually didn't do mass times acceleration, but you get the same equation either way. And so torque can also be a change in angular momentum over time. And then work, I don't know why I have work twice. You can ignore the second work. It's not supposed to be there. And then power is the rate at which work is done. It's the change in energy over the change in time. But we can also find it with a force times velocity. We will go over that at some point in the year when we're reviewing. You can also find it with a torque times an angular velocity. Okay, and we'll dive into that deeper at a later date. Okay. All right, this is your introduction to rotational motion. It's just like the linear motion. We just, instead of mass, we have rotational inertia. And then instead of our linear variables, we swap in rotational variables. Now, the biggest mistake I see students make is that they mix angular quantities with linear quantities. When you're writing your equations or calculating things, we really need to get either everything in terms of angular variables slash quantities or everything into linear variables slash quantities. Okay, so as we go through practice problems, we will be practicing that. All right, thank you for watching.